What I'm going to do today, we went through the black box testing techniques with EP and BVA on previous day. So do a bit of black box testing techniques, decision tables and state transition tables. Just cover that in terms of theory. This afternoon, then what I want to do is very quickly go through this unit testing and JUnit. And then you guys have done JUnit before, haven't you, with Jerry? So it should just a refresh. Did you use the quote service application before?
I don't think so.
I think we did, yeah.
Did we?
Oh, did you?
So.
Okay. I was afraid of that. Anyhow, we're going to. That's what I have set up for today because some of you will know my Java skills are next to nothing. So we'll go through the JUnit test and I will use this quote service as an idea for it. Okay. So that's what our plan will be for the practical this afternoon then at 1 o'clock. Okay. So with that in mind, decision tables. Oops. Okay, so our black box testing, decision tables and STTs or state transition testing. So again, the idea here is that our EP and BVA are normally applied to what we call specific situations or inputs. So you're really looking at a combination of inputs. You're looking at trying to get it really at the kind of the unit test and such. When we look at combination of inputs, there's different combination results and different actions being taken. So that can be a little bit more troublesome in how to demonstrate with EP and BVA. So like if, for example, you are you might, for example, for login, you might be checking to see that the username and password are correct. And if it's not correct, that it's, that's identified. But you wouldn't necessarily be looking to say that if you put in the right username and password, you will then go to this particular type of screen. Or if you put in the incorrect username and password, that you will then go to this particular type of screen. So if you like, the action that takes place is more a result of it's a wider, less kind of partition, less kind of boundary analysis type of situation. So we need some means to be able to try and check what that is so that we can then analyze and properly apply our testing techniques to it. So the typically when we start looking at what we call business rules, which essentially is how is the system supposed to react to a given stimulus within the concept of a business logic or business rules. So typically these decision tables and state transition tables or testing is used for it. So a decision table is essentially a table showing sets of conditions and the actions resulting from them. So there will not be a kind of numeric type response. Okay, it's a good way to deal with combinations of things, so multiple inputs. Testing combinations can be a challenge as the number of combinations can often be very large. So how do you know, like if somebody puts in the wrong email address but the right password, and somebody puts in the right email address but the wrong password, both of them will end up in the same result. Okay, so if you're doing it by the EP and BVA, you tend to end up with a load of tests. Whereas at this level with decision tables, you kind of say, right username combination used or incorrect username combination used. So as we know, testing all combinations is impossible. So we need a systematic way of selecting combinations to test. So they can help in this regard. In conjunction with, it's not as though one of these approaches is better than the other or is done in isolation. Sometimes we need to have the equivalence partitioning so that we can get the right decision for our decision table, if that makes sense. So the first task is identify the suitable function subsystem with a behavior that reacts according to the combination of inputs or events. And once we know what the combinations are going to be, then we can put them into a table and list all the possible results in terms of true and false for each of the aspects that we're looking at. So it's really a combination of the inputs and events and then the aspects that we'd expect from them, or the outputs. So there's one here for a loan application. You can actually the amount of monthly repayment or the number of years you want to pay it back. Okay. If you enter both, the system will make a compromise between the two if they conflict. Two conditions are the loan amount and the term. So we put them into a table as follows. So the condition is repayment amount has been entered, term of the loan has been entered. And then we have a number of rules. Okay. So the rules are, these are, if like the business rules. So the organization has said, right, if you're applying for a loan, then these rules apply. Okay. And they will list whatever those rules are. The conditions are what somebody is looking for in this particular case. So if somebody's looking for a repayment amount or somebody's looking for a repayment term. Okay, so we identify all the combinations of true and false with two conditions, each of which can be true or false. We'll have 4 combinations. So because we've got 2 inputs, it's 2 to the power of 2. So we'll have 4 possible combinations. Essentially true, false, well, false, false, true, true, false, true, true, false, or whatever way you want to work them out there. So we work like that with T and F. Next step is to identify the correct outcome for each combination. So each combination is generally referred to as a rule. Okay. So if the rule 1 true and true, process the loan amount, process the term. If it's rule 2, we'll just process the loan amount. Oops. And if it's rule 3, we'll just process the term amount. And if it's rule 4, which is nothing was entered for either of them, we don't do nothing. Okay. Is there anything missing from this? So the table currently contains outcomes for when the user behaves correctly. What if the customer doesn't enter anything into either field? We can assume that this combination will result in an error message, so we need to add another action. This highlights the strength of the technique in discovering omissions and errors. Okay, so you're looking at it and saying, right, back here. Okay, yes, 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 yes. Okay, here there's no way to say whether or not, there's no outcome to say whether or not this particular combination has been tested or whatever. Okay. So what we need to do is add something first. So we have another one here, error message, which is yes. Oops. We put in there. Okay. If we wanted to prevent a customer from entering both repayment amount and term loan, then we would have a yes here as well, and no, no. Okay, so you wouldn't allow, you'd have an error message here, which may be a different error message. It's up to yourself. So if you're a new customer, opening a credit card is a different one. You get 15% discount on all your purchases today. If you're an existing customer, you hold a loyalty card, you get 10% discount. If you have a coupon, you can get 20% off today, but it can't be used with a new customer discount. Discounts amounts are added if applicable. Okay, so this is kind of the business rules. And sometimes it takes a wee while to get our head around these and actually rephrase it into our own kind of thoughts and our own words. So we've got the conditions here, the 3 of them, and then we start putting in the rules. Okay, and something to note: an X has been recorded as the outcome of rule 1 and rule 2. This means that the combination should not occur. Okay, so we have these 8. We have these 8 conditions because we've got 3 inputs. So it's 3 to the power of 2, which is 8. Or sorry, 2 to the power of 3, which is 8. So we've got essentially our truth table type of things, false, false, all the way up to true, true. Okay. And if I stop clicking the mouse, it'd be better. So what we're looking at here is a new customer, a loyalty card, and a coupon. Can you have that? No. So there's an X there, and the same here where you have a new customer and a loyalty card, because obviously you can't be a new customer and have a loyalty card because they're not permitted. So that tells something, an error message should be flagged there. The discount then is the amount of discount that's been stated. So in rule 3, so this is assumptions. The coupon has a greater discount than the new customer discount. We assume the new customer will choose 20 rather than 15. So this is here where you've got the possibility of 20 or 15. So 15 for a new customer, 20 for a coupon. So in this case, you would assume they will go for the 21. Okay. That is an assumption we're making. So we should check that by asking the person who wrote the specification. Okay. No one, seeing as how it's probably banks and credit cards, they'll probably force you to take the 15%, but that's probably not the case. So for rule 5, we can add discounts since both the coupon and the loyalty card discount can apply. Rules 4, 6, and 7 have only one type of discount, and rule 8 has no discount or 0%. So that's, again, looking at that, rule 8, you're not a new customer, you don't have a loyalty card, and you don't have a coupon, so you don't get any discount at all. Testing based on decision tables, knows cause and effect testing. So you cause something and you check what the effects are. So you're actually capturing the effect and testing it against what you expect the answer to be. To apply this technique thoroughly, we would have one test for each column rule on the decision table. The advantage of doing this is that we test a combination of things that otherwise might not have been tested, and we could find a defect. Normally, and I'm sure you realize this already from your programming experiences, when we get into situations where it's something and something or something or something in terms of conditions, if A is greater than B or if A is greater than or equal to B, that's when we sort of sometimes on the boundaries will run into some problems. So having different combinations are very good. Now, if we have a lot of combinations, it may not be possible to test them all because there is a finite amount of time. Okay. Now, you may need to prioritize and test the most important combinations. Having a full table enables us to see which combinations we decide to test and which we will decide not to test. So we might look at the ones and say, well, actually, that one and that one, they're the ones that probably from a programming point of view could cause problems. So we'll look at them. State transition testing then. State transition testing is used when some aspect of the system can be described in what is called a finite state machine. So the system can only be in a finite number of different states, or a definitive number, a known number of different states. Transition from one state to another is determined by the rules of the machine. So a state transition model has 4 basic parts. States that the software may occupy, transitions from one state to another, events that cause a transition, and actions that result from a transition. So just think of that for the moment, right? You have a piece of software and it's in a state, okay? Now, there may be another number of states. If we take something like a web application, you've logged on, or you haven't logged on, you run it, you're going to register. It's in a state that is ready to register. Your transition then from one state to the other is when you actually hit the button and you start registering. Events that will cause a transition could be whether or not, say that user has already registered, in which case we transition from one state where we're saying, yes, you've registered well, to a state where we're saying, sorry, these details are already used. Also an event could be different, because if obviously the information is okay and hasn't been used before, you transition from the state of being unregistered to the state of being registered. And then actions that can result from a transition. So because of a transition, we're now going to go and show you a particular dashboard or a different setup or whatever. Okay, so that's the general idea with these 4. It's important to get a good grasp of what the state transition events and actions are in your own head. So a simple finite state system, word processor, document is open, you're able to close it. No document is open, then close is not available. Okay. After you close once, you cannot close it again for the same document unless you open the document. So the document has 2 states, opened and closed. Right? In the same way that if you log into a website, you can't log in again unless you log out. So it's the same type of, there are different states. So you have a state that is the logged in state, and you have a state that is the logged out state. And you will find that when you're logged in, you have certain actions available to you. Okay, and when you're logged out, you have certain actions available to you as well. So the finite state is also shown as a state diagram. So we go through an example here of an ATM verification where we're entering our PIN number for the bank account. The states are shown as circles. So again, this is an important part of this whole process. So that we can look at a diagram and understand what's going on, we need to have uniformity between what we're looking at and what somebody else has written, that there's combinations to it. So states are shown as circles. Transitions are shown as lines with arrows, and the arrow is indicating the transition process. So you're going from, logged in state to a logged out state if you hit the log out button. Okay. Events are the text near the transition. We note we've not shown the messages in this diagram. E.g., please enter your PIN. Okay. The state diagram shows 7 states, but only 4 possible events. Okay. So you could have 7 states, but there's only 4 possible events. Card inserted, enter PIN, PIN OK, PIN not OK. For simplicity, we've not specified all the transitions or events. However, the diagram does give us information for techniques, some useful tests, and to explain the state transition technique. So this is what we're looking at here. So the circle is the state, transition is the arrow, you have an event, which is text, and then you have an action. Okay, and what's been shown here is the action has been shown with different colored text. So we've got 1, 2, 3, 4, 5, 6, 7 states. Okay, we've got the start state, card inserted, then it waits for PIN. So when you stick in your card in your ATM, it's waiting there. It'll give you a message to look for the PIN, right? Obviously, when you're getting into lower, if you're checking the process to enter or to, from the display point of view for a PIN, your state transition diagram might expand a little bit more for looking for different things. If I hit the number 9, that the number 9 is what's been entered and that kind of stuff. You then enter a PIN and you get the first try. So that's the state. If the PIN's okay, it goes to the access account. If the PIN's not okay, it goes to the second try. Then the second try could well say, sorry, incorrect PIN number, you have 1 try left, or something like that, or 2 tries left. If the PIN is okay that time, it goes to access account. If it's not, it goes to the third try state, in which case it'll probably a little bit more forcefully say, this is your last chance to enter your PIN. And if it's okay, you get to access account. If it's not okay, it'll swallow the card and you won't get access, or whatever the conditions would be. Okay. Generally, a number is assigned to each state, so it'll be state 1, 2, 6, so forth. Okay. And typically that goes left to right, although it can get very confusing. Particularly, this is a fairly straightforward one, so you can imagine it being 1, 2, 3, 4, 5, and then 6 or 7, whatever. Okay, but sometimes you'll have quite a number of parallel lines, and it's more difficult to get a system in place. Okay, there should be some form of logic to it. Okay, hopefully. So you start with testing the ATM system. You start with a typical scenario, which is possible. Sensible first test would be the normal situation where the correct PIN is entered for the first time. To be more thorough, we may want to make sure that we cover every state. At least one test goes through each state, or cover every transition. So visiting every state would be to enter an incorrect PIN each time, which would hit eventually the incorrect PIN state, which would have the system swallow the card. To test every transition, we would want a test where the PIN was incorrect the first time, but okay the second time. Another test would be the PIN was incorrect the first 2 times, but correct the third time. Okay, so looking at this here, we're saying, right, one method is to go with the correct PIN. So you go here, first try, bang. The second one is to go with an incorrect PIN 3 times. So it goes 1, bang, 1, 2, 3, and then swallow card. So every state has actually been transitioned there in both these cases. The full comprehensive test would be to go all the way through here, then all the way through the right pin, then a wrong pin, or sorry, a wrong pin, then a right pin, and then all the way through here, right pin, wrong pin, and so forth. So you try them all. So an advantage of the state transition technique is that the model can be abstract or as detailed as you need it to be. So it depends on what level you're at. So if you're up at a system level, it can be a bit more abstract than it would be if you were down at a lower level. Part of the system is more important, that is, it requires more tests and greater depth of detail may be modeled. Okay. So if you're looking at actually getting access to the account, you might want to look at that in a little bit more detail. Okay. See where there might be flaws in it. And where the system is less important, requires less testing. So that's, if you think of it in terms of an ATM, you're testing the machine. Getting access to the account and actually swallowing the card are two different things. Okay, in terms of there's mechanics and so forth associated with swallowing the card. Then we create our state tables. Deriving tests from state diagram is good for seeing all valid transitions. Where we try to generate invalid transitions. So state diagrams do not easily demonstrate negative tests. Okay. In order to see the total number of combination states and transitions, both valid and invalid, a state table is useful in that sense. Probably the most important part of the whole thing is that when we look at it, we can actually physically map through that we're going through every state possible, which I think is probably the best part of the whole thing. So we have situations here. So we've got our 7 states. We've got a number of actions: insert card, valid pin, invalid pin. So state 2 is wait for pin, invalid pin, or sorry, valid pin, it'll go to S6, invalid pin go to S3. First try, valid pin, S6, invalid pin, S4, and third one is there, and it goes S7, third try, invalid. Access account, question, swallow card, S1 for new card. So it goes back into the start state. Okay. So we've put this the invalid state test will attempt to generate invalid tests. Okay, so it's transitions that shouldn't be possible, but often make good tests when it turns out that they are possible. So it's always worthwhile there. So in this case, we've put in the dash here. Like, what happens if for an invalid pin, or sorry, a valid pin on the third try? You know, what's the story? There's no real course there because it's going to S7. Put a question mark 2 cells where we can enter either a valid or invalid pin when accessing the account. Perhaps the system should take our pin number as the amount of cash to withdraw. It might be a good test. So again, there's interesting things you can look at there. And use case testing. Is a technique that helps us identify test cases that exercise the whole. Okay, I think I'm back there. The internet must have dropped or something there for a minute. Where are we? So sequence of steps there, mostly a system and acceptance test level. So this really is because you're looking at a high level here where you're actually interacting with the system rather than at a low level where you're actually down with the with the actual unit test in itself. Okay. Use case describe the process flows through the system as it will most likely use. Okay, and that most likely use is underlined there for a reason because that's what we think it should happen. Makes the test from use case particularly good at finding defects that the user are most likely to find. Okay, because typically what happens is we build all these little blocks together and then we expect the whole thing to work. Okay, and we don't necessarily get it from a user's perspective as to, well, this is what I would normally do. Okay. Like there's nothing in that diagram that's given there where we actually say, actually, after the second time, I better go back and check what my pin is. So I won't actually eject the card and leave. So that's something that I know would happen sometimes if you've got your number. The pin example can be used for state transition tests. It could also define in terms of use cases for a success scenario. A test for each extension representing the ways in which the scenario would fail to be a success. So we're kind of looking at the opposites there in that sense. So here we have the main success scenarios 1, 2, 3, 4, 5. So inserts the card, validates card, and asks for PIN, enters PIN, validates PIN, allows access to the account. So the extensions would be 2A, right? So you've got the, we have here the A is actor and S is system, okay? So A, the actor being the person, the tester. 2A, card not valid, S, display message and reject card. 4A, S, validates PIN. PIN not valid, S, display message and ask for retry twice. And then 4B, PIN invalid 3 times, S, swallow card and exit. Okay, whoops. So essentially what we're looking at here is this is the success scenario, and then the extensions are where there are cases where the normal success scenario doesn't take place. So we're looking at the step, and the A there is not the first one, it's just A is for the actor, and then the A is for that, isn't it? So we could have an A and a B and a C.